Hello and welcome to EngPhys 3004 lecture number 14, starting off with heat conduction in cylinders and spheres, continuing on with our steady state heat conduction. For cylinders and spheres, the idea is that, as before, in steady state, heat doesn't build up anywhere. So all the heat that conducts from the inner surface to another surface of a cylinder must continue on. So the heat flow through any surface is going to be equal to a constant as we move out through the cylindrical shell here. And from that being a constant, we can substitute in the area of each of those shells and then solve for the temperature distribution, which then gives us, once we substitute it back in, that the heat flow has to be equal to 2 pi Lk over the difference in temperatures divided by the natural log of the ratio of radii. This is outer radius of the cylindrical shell divided by inner radius. For a spherical shell, we could do the same thing and end up with a slightly different formula. The rate of heat flow in steady state conduction through a spherical shell is 4 pi thermal conductivity, inner radius times outer radius divided by outer radius minus inner radius times the temperature difference across the spherical shell. Proceeding as we did in plane walls, we can then define the rate of heat flow as the temperature difference divided by the thermal resistance of the cylindrical or spherical shell, which then leads to these formulas. Thermal resistance of a cylindrical shell is the natural log of outer radius divided by inner radius over 2 pi Lk, and for a spherical shell, it's outer radius minus inner radius over 4 pi K times the product of the radii. For multiple layers of cylindrical or spherical shells in kind of around each other, these would just be in series, so you'd add them up. And if you have kind of a convection inner surface plus a cylindrical shell conduction, then a convection outer surface, again, these would all just be in series. Okay, suppose we're insulating a cylindrical pipe. The equivalent resistance for the insulation plus convection at the outer surface would be the sum of them in series. And substituting in the area of the outer surface for convection, we see something neat happen that didn't happen for plane walls. The area of the outer surface increases with increasing insulation thickness, and that means the convection resistance goes down as we increase the insulation thickness. That's a new thing. For plane walls, adding more insulation didn't affect the convection resistance because the area is the same. It doesn't change as you add a thicker insulation. But for cylinders or spheres, it would. And this means that adding insulation can actually increase the rate of heat transfer from that surface if the convection increase is overpowering the increased resistance from conduction, and that's kind of surprising. So where this balance happens, where you have the minimum point of thermal resistance, where the radius that happens at, the outer radius that happens at, is called the critical radius of insulation. We can find that by taking a derivative of this with respect to the outer radius and setting that equal to 0 to look for our critical points. And for a cylinder, this occurs at K over H convection. So not surprising, this balance is minimized. So the radius that gives you the minimum resistance occurs at a large radius when we have a lot of thermal conductivity of the insulating material and a low convection coefficient. So if convection is relatively small compared to conduction, then adding more insulation will make things worse. But if convection is very large compared to conduction, so we've got a good insulator, then adding more insulation probably makes things better. Again, this balance happens. This critical radius is the radius where the resistance through conduction and then convection for a cylinder or sphere is minimized. This is only the formula for a cylinder. There's a different one for a sphere, but you find it in the same way. You figure out what the equivalent resistance is by adding those two in series, and then take a derivative with respect to the outer radius and set that equal to 0. Why it occurs is because adding more insulation thickness, while it increases the resistance through that insulation from conduction, it also increases the heat flow from convection, or decreases the convection resistance at the outer surface. All right, on to lecture 15, which is heat transfer from finned surfaces. If you look at the convection equation, so the convection heat transfer equation, the heat flow from convection is H times the surface area times the difference in temperature between that surface and the free stream. So one obvious way to increase the convection is to increase the surface area. And the typical way to do that is with fins. So here's some fins on a stegosaurus that had a lot of blood flow through them, presumably for cooling rather than defense, as was previously thought, and some fins for heat sinks in integrated circuits. There's car radiators as another example of ways to cause a lot of surface area to increase the heat flow using fins. So in this section, we're going to look at solving a differential equation called the fin equation. And this comes from this sort of a geometry. You've got a base temperature, and the differential equation is in temperature. We're going to look at how the temperature changes with respect to x along the length of some fin. And the basic idea is any element of the fin of length dx and cross-sectional area AC must have the heat that flows into it from the section closer to the base from conduction is balanced by the heat that flows out of it to the next section and the heat that flows out from convection from its surface. So P is the symbol for the perimeter of that section. And so the surface area would be P times dx. Okay, now if you take the balance of that heat flow and substitute in that the conduction from one section, the conduction at any point is negative Ka dt by dx, then you can come up with the fin equation. So there's a derivation of that below. I encourage you to try it for yourself. What we're going to do now is look at solving the fin equation under a number of different boundary conditions. So the first special case that we're going to do is we're going to assume that we've got a constant cross section, so just a rectangular fin, and constant thermal conductivity, so that we can take the Ka out and turn this into a second order differential equation, like so. Then we're going to take T infinity, the free stream temperature of the fluid, as a constant, so that we can substitute that in for the derivative in the first term and make the substitution theta. Theta is equal to T minus T infinity is the temperature relative to the free stream temperature. And the reason we do that is because this variable substitution is a homogeneous second order differential equation with constant coefficients then, which you can solve from your second year differential equations course material. Okay, so how you solve it is by substituting an assumed form of e to the mx, and once you substitute that in, you find that there's two different solutions, c1 e to the e to the positive mx and e to the negative mx, and then you take a linear combination of them to get the general solution c1 e to the mx plus c2 e to the negative mx. And to solve for those constants, those coefficients, what you need to know are some initial or boundary conditions. And we're always going to use that T at the base is TB, so that's a constant in steady state again, and uniform over the base. So theta at 0, the x coordinate of the base of the fin, is TB. And what we're going to use for the other end is dependent on which situation we're solving. So we're going to look at infinitely long fin tip, adiabatic fin tip, which means no heat transfer from the tip, specific fin tip temperature, and convection from the fin tip, which is the most likely case, but it's very difficult. So first, just to get a feel, you can try out this first one, infinitely long tip. That means that theta as x goes to infinity has to be equal to 0. Remember that theta equals 0 corresponds to T equals the free stream temperature. Okay, and that leads to the first coefficient being 0, because you can't have a positive exponential term sticking around if it's got to go to 0 as x goes to infinity. So that means that C2 has to be the value at the base, and we end up with this temperature distribution. To find out what the rate of the heat dissipation by the entire fin is, you substitute in x equals 0 to the heat transfer. Now the heat transfer from conduction is negative Ka dt by dx. So we need to take negative Ka dt by dx and then substitute x equals 0 into that using the temperature that we just had. So this is the temperature distribution, but again, what we're more interested in is the total heat dissipation by the fin. So taking the derivative of this temperature distribution and then substituting x equals 0 leaves us with the heat dissipated by the fin as the base temperature minus T infinity times root of HPKAC. Okay, so this is the infinitely long fin result. We've got two things that we're possibly interested in, the temperature distribution and then the total heat dissipated by the fin. The adiabatic fin tip, meaning that there's no heat dissipated by the fin tip, leads to this boundary condition dt by dx equals 0 at the fin tip, because if it wasn't 0, then you would have conduction at the tip. Okay, so this boundary condition is a little bit more involved to solve, but you just substitute in the condition to the differential equation along with the theta at 0 equals theta b condition, and after a little bit of manipulation, that leads to the theta at x being theta b cosh m times L minus x over cosh ml, where m is again equal to the square root of HP over KAC. So substituting back in what theta was, T at x minus T infinity over TB minus T infinity is cosh m L minus x over cosh ml, and the heat dissipated by the fin proceeding as we did before by taking the derivative, multiplying by negative Ka, and then substituting in x equals 0 gives us this formula. So the result is actually similar to the infinitely long fin, but with a tan hyperbolic at the end of it. Now, as you would expect when you take L towards infinity, in this tan hyperbolic term, you limit towards 1, and that means that the heat dissipated by an adiabatic fin tip case in the limit that L goes to infinity limits to the same as the infinitely long fin, as you would expect. All right, so moving on to the last two conditions, we have a boundary condition of a specified fin tip temperature, which would lead to this temperature distribution and this total heat dissipation, a little bit more complicated than the adiabatic tip. And finally, convection from the fin tip, which is probably the most realistic case, leads to this quite complicated temperature distribution and quite complicated total heat dissipation. Now, rather than using these, it turns out that these formulas, the temperature distribution and total heat dissipation, are almost the same as the adiabatic case, as long as you use the corrected fin length rather than the actual fin length. So that is, rather than model the convection from the tip using the complicated formulas, you can say, it's the same total heat dissipation as an adiabatic fin would have, as long as you add in a length so that you add back in the area of the fin tip, since you're removing that here with the insulated case. That's almost the same results for the heat dissipation. Okay, now for two figures of merit that people talk about with fins, the fin efficiency and the fin effectiveness. Fin efficiency is the ratio of the heat dissipation by the fin to the heat dissipation the fin would have if it was all at the same temperature. So when we started this off with fins, we said, hey, you know what we should do is just have a lot of area for the fin, and that will cause a lot of heat dissipation. But what we found out from the differential equation is that we don't have quite that much heat dissipation as the area of the fin, surface area of the fin, times the difference in temperature between the base and the fluid, times the convection coefficient, because the temperature at the surface of the fin is decreasing along the length of the fin, since the situation that leads to lots of aspect ratio, lots of area, also leads to generally narrow fins that kind of limit conduction. So there's probably a balance for that. You don't want to use a whole lot of material, but you want to have a lot of surface area still, and that means that generally your fins are going to be pretty thin and have non-perfect efficiency as a result. So again, fin efficiency is the ratio of the actual heat dissipation by the fin to the heat dissipation the fin would have if it was all at the base temperature. All right, so once you've got this, you can, this idea, you can substitute in the heat distributions that the temperature distributions we just had and the total heat dissipations that we just calculated for, say, the long fin, and find out that efficiency is 1 over ml, or the adiabatic tip, tan hyperbolic of ml over ml. These both have the property that as length gets longer, the efficiency goes down. And that makes sense because the thing that's limiting the efficiency is the surface of the fin not being at the base temperature. As you make the fin longer, that becomes more and more of a problem. The longer the fin, the less of the fin is going to be at the base temperature, and the lower the efficiency. But efficiency is not the only story. The other thing that we need is the fin effectiveness. Fin effectiveness is how much total heat dissipation we have from the fin compared to the heat dissipation we would have with no fin. Now, unlike efficiency, which has a limit of 1 in theory, the effectiveness has no real upper limit. So the longer you make the fin, the more heat dissipation you can get from it in theory, and have more and more complicated fin designs. Better conductivity means you can have more and more heat dissipation from the fin. The effectiveness, again, ratio of the heat dissipation from the fin to the heat dissipation the surface would have with no fin, which is just H times the base area times the difference in temperature. Comparing these two formulas, you can see that efficiency and effectiveness are related. So efficiency is the heat dissipation of the fin divided by heat dissipation without the fin, which is substituting in heat dissipation by the fin from the efficiency definition, eta H area of the fin times the difference in temperature. Now the difference in temperature and the convection coefficient cancel, so we have that the effectiveness of the fin is the area of the fin divided by the area of the base times the efficiency of the fin. This is, again, assuming that the convection coefficient that the fin is subject to on average is the same as the convection coefficient the base would be subject to without the fin. And that is a huge assumption, which we're going to address in more detail in chapter 19. But at least for now, assume the convection coefficient is constant for the purpose of this analysis. Okay, so making the fin longer leads to more heat dissipation, but the amount of heat dissipation that happens starts to trail off as you add more and more length to the fin, because the temperature starts to go more and more towards the free stream temperature. So making the fin infinitely long doesn't really give you infinite temperature unless your conductivity stays up there. So you can see what happens here to the heat dissipation by the fin compared to the heat dissipation of an infinitely long fin as you increase the length of the fin. Once you have m times L equal to 5, you're at pretty much 100% of the heat dissipation you're going to get. Even 4 is at 0.999 of the heat dissipation you could get by making it longer. So generally, this is way too much ml, way too much length of the fin, because if you were to, say, cut it in half to 2, you would only drop the heat dissipation by the fin by a factor of less than 4%, so 3.6 or so, 3.5% compared to the fin being twice as long, which means you could save a lot of material and have about the same dissipation. Generally, for most practical purposes, ml equals 1 is about the proper length of the fin, and that corresponds to a heat dissipation of 76% of the heat dissipation you could get if it was infinitely long. The very last thing we're going to talk about is our heat sinks. Heat sinks are designed objects to dissipate heat, and there they generally talk about the thermal resistance of the heat sink as a characterization parameter. So the total heat dissipated by the fin is base temperature minus the free stream temperature. Now if we define that divided by the resistance, then you could see how the thermal resistance of a heat sink is related to the efficiency and and other parameters that we defined earlier. So heat sinks are kind of combined elements. They're made up of series of fins distributed over a surface. Now you'll notice one other thing in this section. They're giving you different dissipation amounts by different resistances, depending on whether these fins are oriented horizontally or vertically for some of the designs. So you'll notice that the vertical orientation leads to less resistance, and that means more heat dissipation than the horizontal one. What this is talking about is vertically aligned so that the fins are along the vertical direction themselves. So that is a lower resistance because natural convection can cause more heat flow through the fins, and that helps with the fluid motion, effectively leading to a larger convection coefficient and therefore more heat dissipation.